In this video, we will be discussing how to use the time-shifting theorem, also known as the t-shifting theorem, in finding the Laplace transform of a shifted function. So, let us first define what a shifted function, or more specifically, a t-shifted function is. An unshifted function looks like this, f of t. A t-shifted function, however, means that your t here is shifted a units. So you replace your t here with t minus a. So to give the definition of a t-shifted function according to the t-shifting theorem, a t-shifted function, denoted by f tilde of t, is just equal to f t minus a u t minus a. So see that the t minus a here is reflected here. The shift by a units is reflected in this definition of the shifted function. So you must be confused as to this part of the expression here. So this is actually a unit step function, which I will show later how it plays a crucial role in finding the Laplace transform of a t-shifted function. Getting back to the equations, so when you apply the definition of this unit step function to f tilde of t, you will get f tilde of t is equal to 0 if t is less than a, and f of t minus a if t is greater than a. So you're able to get this definition of the shifted equation because of the unit step function here. So that is the definition of a shifted function, of a t-shifted function. So after establishing that definition, we will now use the t-shifting theorem to find its Laplace transform. So given that the Laplace transform of a regular unshifted function is capital F of s, the Laplace transform of a shifted function f tilde of t is equal to e to the negative as f of capital F of s. So notice that the capital F of s here is just the Laplace transform of a normal unshifted function. This means that the shift in the function is reflected by the e to the negative as factor over here. So it is taken care by this e to the negative as factor here. So taking note of this makes calculations a lot easier because now you just have to find the Laplace transform of the unshifted function and multiply that by e raised to the negative as. So alternatively, for functions with a slightly different form like this one, f of t u t minus a, you can find the Laplace transform of this, still using the t-shifting theorem. This is just equal to e to the negative as times the Laplace transform of f t plus a. So it is now t plus a. So this may look different from each other, but these two are actually just equal to each other. It's just another form of solving for functions that have a slightly different format. So as mentioned earlier, I will explain how the unit step function plays a crucial role in finding the Laplace transform of a t-shifted function. So, giving the proof of the t-shifting theorem, we will start with the Laplace transform of the t-shifted function, which is e raised to the negative as times capital F of s. So, using the definition of a Laplace transform, e to the negative as, this is just equal to, since this is the Laplace transform of f of t, and using the definition of this and multiplying it to this factor here, this will be equal to e to the negative as times the integral from 0 to positive infinity of e to the negative s, let's use the variable q, f of q dq. So this is basically the definition of the Laplace transform of f of q. So the next step here is that we need to put put e to the negative as inside the integral function. So this will be equal to integral from 0 to positive infinity e raised to s times q plus a multiplied by f of q dq. So letting t equal to q plus a, this will now all become, since we introduced a change in variable here, the limits of this integral function will change too. However, only this will change and the positive infinity remains unchanged. So this will become integral from a to positive infinity e to the negative st f. Q will now be t minus a dt. So recall from the definition of a Laplace transform, we can only apply the definition of a Laplace transform if the lower integral here is 0, like this here. So in order to change the lower limit to 0, we need to multiply u t minus a here. So doing that, so let's do that. So this will now be equal to integral of, because we will multiply u t minus a to f of t minus a here, the lower limit of this integral will now be 0. Upper limit is still positive infinity. E raised to negative s t f t minus a, multiply the step function here dt. So if you notice, this is actually just f tilde of t, right? So this will now be equal to e negative st f tilde of t dt, which if you can now notice, we can actually now use the definition of a Laplace transform for this in this equation. So this will now be equal to e to the negative as f of s will now be equal to the Laplace transform of f tilde of t. So there you have it. That's the proof for the t-shifting theorem, and that shows why this unit step function here is crucial in finding the Laplace transform of a shifted function. Now that we've established the definition and proof for the t-shifting theorem, it's time to answer some questions and problems. So first here is finding the Laplace transform of the shifted function t minus 2 u t minus 7. So what I like to do is I always tend to use the alternate definition for the t-shifting theorem, which states that the Laplace transform of a function f of t u t minus a is equal to e raised to negative as times the Laplace transform of the function f of t plus a. So I find this much easier. So first what I do is, so I write out f of t, which is this function here. And if you look at the given problem, this is t minus 2. So this is equal to t minus 2. The next thing I do is find f of t plus a. So if you notice here, a here reflects to the number 7 here. So a therefore is equal to 7. So f of t plus a is equal to f of t plus 7. So substituting t plus 7 to this t here, we have t plus 7 minus 2, which is actually just equal to t plus 5. So f of t plus a is equal to t plus 5. So next thing I do is, what I like to do is to follow. So now I follow the definition for the t-shifting theorem, which states, so now according to the alternative definition for the so according to the alternate definition for the t-shifting theorem, this would all be equal to e to the negative as, which in this case a is 7, so 7s, multiplied by the Laplace transform of f of t plus a. So f of t plus a, as we just found out, is equal to t plus 5. So this is t plus 5. So getting the answer for this, e to the negative 7s multiplied by the Laplace transform of t, which is just 1 over s1 plus 1, plus the Laplace transform of 5, which is s. So we have e to the negative 7s 1 over s squared plus 5 over s. We have e to the negative 7s 1 plus 5s over s squared. So therefore, the Laplace transform for this shifted function t minus 2u t minus 7 is just equal to 1 plus 5s over s squared times e7s. So that is how we obtain the Laplace transform of the given t shifted function.